Okay, today we are going to talk about Lab 5. Okay, the Lab 5 is the discharge measurements and open channel flow sluice gate. So unlike Lab 3 and Lab 4, we're using the pipe system to do the experiment. This time we're going to use the main channel. As many of you guys may already see, the main channel is sitting in the longitudinal direction of the lab, which is 36 feet long. It's a rectangular channel. Consists of two sections. The first section is right beneath the head tank, which is wider, three feet wide, but it's kind of short. It's just 10 feet, 10 feet long, um, 3 feet wide, and the rest of the part is 1 feet wide. Okay, so this time we're gonna put the water into the channel and manipulate with the sluice gate. We create the water depth difference and applying the Bernoulli equation and calculate the theoretical value of the flow rate. Okay, so since it's the first time I'm doing this kind of a video instruction, I'm pretty nervous because I'm putting everything with, I need to combine all the video clips and put my voice, which means I add the voice into the video. So probably we will have some synchronizing problems. So my voice will not exactly follow the video instruction. So please kindly bear with me. Okay, so if I do miss some important part which cause you some difficulty to understand the material, please feel free to let me know. Either shoot me an email or Slack chatting, or even on Thursday we have a QA session. I will hold for 1 hour and a half, so we can discuss about the details, the difficulty you have in this lab. Okay, so let's move to the next part. I will briefly introduce the basic idea of this lab. Okay, here comes the apparatus. So we're going to talk about the equipment we are going to use in this lab. Okay, so still we need to use our pump. Okay, so this is our main pump, which is responsible for the water circulation in the slide. So you guys may know the underground storage pump, right? It's filled with the water. Okay, so if we start the pump in here, it will draw the water into the pump and deliver all the way up to the head tank. Okay, because the pump is very powerful. So basically it can maintain the head tank full, right? And I already told you guys, if the head tank is full, there's a spillway on the side, so the water can come out, from the spillway and back into the storage pump. So it's kind of a circulation. Okay, the reason we need to have a full head tank is because we want the head tank maintain the constant head. Okay, because as you see in here, there's a valve, right? The vertical pipe and a valve. The valve is used to control the opening in this pipe and determine the flow rate coming down from head tank to the flume. Okay, so if we open the valve to a certain degree, the water will coming down into the channel. So if the head tank is not full, we open the valve, the flow here the flow rate could not be a constant. So that's what we don't want. that's something we really don't want to happen, because if it happens, we're hard to doing a measurement, because what we want to have is a stable water surface so we can do the measurement. Actually, we have a, this region is the region of our interest. The the main idea of this lab is we use this sluice gate. Okay, we lower and just manipulate the opening of this sluice gate. We can control the water depths in this head box and in this channel. Okay, so as you can see in here, if we let the sluice gate fully open, so the water will come into the channel freely. It will flow all the way through the channel and coming back to the pump. Okay, because of the pipe is still working, the water will go all the way back to the pump, which create a current in here. So as many of you can see, we also have a partial flume in this experiment. So it's not in the sketch, but I will let you know the idea of the partial flume. So the partial flume is just a device in here which can, empirically measure the flow rate in the channel. So if we know the height in here, the H, so once we know the water depths in the partial flume, and we plug this H into this empirical equation, it will give you the flow rate. And since the water is circulating, right? The water is circulating. So the Q in here must equal to the Q in the channel. So this Q we calculated is actually the Q measurement, okay? And you may already know this is a Q measurement, and to be compared with the Q measurement, we need to have the Q theoretical, right? And the Q theoretical is something we are able to acquire by manipulate with the sluice gate, get the water depths in here and here, and use the Bernoulli equation to solve the Q theoretical. So after that, data analysis will be compare the Q theoretical with the Q measurement. Okay. Okay, here is the profile and the plan view of the area of interest. Okay, which is the area which is the upstream of the sluice gate and downstream of the sluice gate. Okay, here we can see, the head tank is giving the water into this part. Okay, so this part we call it head box. Okay, which is 3 feet wide. Already talked in the previous video clip. And you see here the water will coming down from the head tank, enter the head box, and here is a rounded entrance, and the sluice gate is right in here. Okay, if it's fully open, the flow will go through the rounded entrance into the 1 feet channel in here freely. So initially, without the interference of the sluice gate, the water surface should be, equal. The H1 should be equal to the H2. Okay. So what we're gonna do in this experiment is we trying to control the sluice gate to a certain degree. Like if we lower the sluice gate cut in the middle of the flow, see, the water will be pushed by. So the water depths in the head box will increase. And on the contrary, the water in the main channel, the water depths in the main channel will decrease. Okay. And if the water depths upstream and downstream become stabilized, we are able to get the H1 and H2 in here. And also we have our B1 and the B2. That's very important. So once we had all these, geometrical values, we are able to calculate the flow rate, the theoretical flow rate, by using the Bernoulli equation. Okay. Well, it's easier to say than actually doing it, because in reality it's very hard to maintain a constant H1 or H2. Okay, because the head tank has the water coming down, and the big pounding force will let the surface fluctuating like this. So in reality, it's very difficult to measure the H1. Okay, and also because if you lower the sluice gate, it's really hard to say. If you lower to a certain degree, let's say the opening here is 1 feet. Okay, so how can you make sure the flow rate from the head tank, could actually maintain the water elevation in the head box stable? I mean, it could increasing, continuously and cause the overfill in head box, right? So actually, we're trying to look for exact flow rate. I mean, in certain type of opening, there is only one flow rate will give us a stable H1 and H2. And what we can do is, you see the valve in here. During the experiment, we're not going to change the opening in here, because it will makes everything complicated. So what we're gonna do is we have another valve in here on the side of the head box. So we open or close the valve in here. We control the water coming out from the head box, right? So if the water depth in the head box is increasing too fast, we try to open it more to lower the water surface. So it's kind of a try and error. So eventually we will have the H1, or I mean the H1 is uncertain, of course. What we will see is once you are observing the head box and the water elevation is not moving, or it's moving very, very slow. Well, at that time, you can do the measurement of your H1 and H2. But it's really hard to do it. You need to try a lot of times to find, by controlling this valve to get the exact flow rate can meet the equilibrium condition. Okay.